Well, good morning. And today we will try to conclude the part which is devoted to the model validation. So to understand if the selected structure and order are were selected in an appropriate way. So another way to understand if the model so in the previous lecture, the last week, we saw a different methodology for determining if the selected model was appropriate. Especially they were based on a statistical test, which check if in principle, if the residual is uncorrelated with respect to itself. And so, in order to see if the residual is a white process, and if it's uncorrelated with the input, because if you remember, if there are some influences in the residual of the input, it means that you didn't do a good job selecting the structure and the order. And so we will see in the next lecture how to use different, at least suggestions for understanding if the selected model is fine. So another way for at least having a suggestion if the model is too complex, so it means that if you perhaps selected an order that is too high, as is remarked here, so if the model is called an over-parameterized, so it means that you choose a number of parameters that are too high. So it means that the model is unnecessarily complicated, and because it uses more parameters than the minimum number needed, so it can be more sensitive to parameter variations. Is something that should be clear, because if it contains too many parameters, it means that if there are some uncertainties affecting these parameters, and because the model is additive, so the uncertainty is entering in the model, and so you have a more sensitive effect to the parameter variations and uncertainties. So it's a very simple way to understand if perhaps you selected a number of parameters that is too high, is to, and if you remember that the model is in its transfer function form, so by checking the pole and zeros, you should understand if the number of parameters is too high, because if you think that when you introduce in your parameterization too many poles and zeros, more than required, so the only way for the model to check to warn you that there are too many poles and zero is implemented by introducing a pole zero cancellation, because if you are entering an extra pole, the model automatically includes an extra zero that cancel out this pole. So in this way, the model suggests that perhaps a lower order is a suitable order for the system. So let's see an example. Of course, you must take into account the uncertainties in the poles and zero, but this is, for example, a clear indication. So for example, here in this in the plot on the left, you see that there are three poles, one real and two complex. So it means that this model is an order n equal to 3, because it has a real zero and a real pole and two complex poles. But if you try, for example, an order that is 5, so you include two extra poles, and you see here that the model in an automatic way introduces two zeros that should cancel out your poles. Of course, the previous ones remains as is here, that they're the same poles and zero of the previous, and the other one is unnecessary parameter, so is something that you need to remove. And if you notice here in the structure, normally the way for indicating the number of parameters is that you use this way, where you normally include the first number is the number of poles, which is 3, and the second number is the number of zeros minus 1. So you have always a number of 1 unit of difference between the poles and zero. And the same here, you have a model of order 5, and here you have a number of zeros minus 1, because it's like a convention it's a way of showing, of highlighting the number, which is because it's connected to the number of the parameters. So normally when you check the number, there is a function in the toolbox, there is a menu, you depict the number of poles, also the position of the poles and zeros, and of course it's not always so clear like in this way, but perhaps of course we will see that every pole is normally, or zero pole is always associated with an uncertainty, so perhaps it's close, but not like in this case they are perfectly aligned. But this is a clear indication, that is a clear warning that the model is saying that these two poles are not required for modeling, because they are cancelled out by the two zeros that the model is including. But we will see this case in when we will examine the example of identification of a model. Or cross-validation. Cross-validation is something that you should perform, as for the case, if you remember, with neural networks. Cross-validation means that normally you should test if you can. Normally is we will see in our toolbox, we will use a set of data that are used for the estimation, and a second set of data which is used for the validation. So this is called the cross-validation, because you are checking the behavior of the model with respect to another set of data that you have not used for the estimation. So normally, in order to do this, you consider, if you remember, the Cost function, normally if you remember, cost function can be one step ahead, is indicated here. V with the subscript 1 means that this cost function is computed with the estimation error obtained by the one step ahead prediction, or in general with K step ahead predictions. Not only one, but if you remember, the more samples you are going ahead, the more the model is accurate if this index is low. So perhaps the model structure that you have selected is too rich. So too rich means it contains too many parameters to describe the system, to describe the real data. So if your model is too rich, it means the order is too high, so you are perhaps modeling also the disturbances that you don't need to perform this modeling, this description. So you are modeling also the disturbances that are present in your data. This is called, if you remember, is the same condition when we talk about the overfit of a neural network. A neural network overfits the data when it's trying not only to model the real information of the data, but also the noise. A typical example, if you remember, was the radial basis functions. They are perfect interpolators, but they are also describing the noise if the number of centers was too high. So normally, how you can try to avoid this problem of considering a model that is too rich, so rich in the sense the order is too high. So normally you should use let's say, it's called here fresh data set, means that is a set of data that are not used in the identification. So this is why it's called cross-validation. So you are using a different set of data that they are used for the identification. And the cross-validation is a nice and simple way to compare models to detect overfit models. So folks, of course, perhaps you are not able to do it always, because in some cases you have a reduced number, a limited number of data, for example, only 100. So the best solution is to consider all the data for the identification, because if you, for example, you have only 100 data and you split into two sets, 50 data for the identification and 50 data for the validation. 50 data is a too limited number of data for performing our estimation. So in these cases, normally you use all the same data for both the validation, the estimation and validation. But in our cases, you can generate the number of data that you require. Normally you can obtain 1,000, perhaps also 10,000. We don't have problems when we are generating the data by our own. Of course, as this slide concludes, normally cross-validation requires a large amount of data. So the validation data cannot be used for the identification. Of course, if you have a reduced number of data, normally you use the same data for the estimation, for the validation. But if you have enough data, so please use two different sets of data. So this introduces what we call the parsimony principle is a principle which is it was introduced also in philosophy, not especially in this field, but so we reuse this principle, and is saying very simply that if one should not use extra parameters to model a system if they are not necessary. So if you can obtain something which are reduced with a reduced number of parameters, sorry, please do not use more parameters. If you can obtain the same solution with a reduced number of parameters. So do not waste time or parameters. So normally we assume the quality of the model by another function, which in case is called Wn. Wn, if you can understand clearly, that is the expected value of your error, squared error, and epsilon is the prediction error. Of course, you remember that if the estimate is the same, of course, this holds only in theory, because normally you don't know this vector is unknown. But in the case that your estimation is the same of the true vector, the prediction error is white, and this value, this W, is the same of the noise affecting the data, of the standard deviation of the noise, lambda squared. On the other hand, when theta n estimated is different from theta 0, because it is always, perhaps as we already remarked, maybe theta 0 is not existing, it doesn't exist. So this parameter is different from the noise affecting the data. So results, we can introduce, yes, some researchers introduced, in order to measure this cost function, it can be shown that the expected value of this function, of this indicator, is equal to the cost function, is the, if you remember, this is the mean square equation error, plus this parameter, and W, this V1 is equal to this value. It can be estimated. So you can you have this is a performance index. If you can see here that this performance index can be represented by, in order to show you, I can plot it. With respect to the number, P if the number is the number of parameter, this performance index was already remarked in some previous lecture. So you have something that depends on the cost of the model order. So this is a straight line, something like this. This one. And because you see here that is a weighting of the order of your model. So this cost function increases linearly when you increase the number of parameters. And the second function, I can plot it in blue. This one, so this is in red, this is in blue, is something that has this, because if you remember, when you increase the number of parameters, the equation error, the mean square equation error is decreasing because you increase the number of parameters. So this function, this one, which is, I can show you, this one can have this form, something like this. So it indicates that there is an optimal number. I can call it P star, which is the optimal number of parameters. If you are able to depict this function, you can also, this is the expected value of W, and so if you are able to depict this function, you have an idea, an indication of what is the optimal number of parameters. We will see that for the case of AREX model, you can obtain this function before estimating the parameters. So it's something that is very useful. But it holds only for the AREX models, so something that is very simple. In order to compute this for Armax Boxe-Jenkins, you need to estimate the parameters and then to compute for every order this function. So it's something more complicated, but is an advantage for the AREX models if you can plot in advance like this cost function. We will see it that we have some indicators that can be used for having a suggestion on the order of the model. So as a note here, the expected value of this function represents the average of the estimates models that are evaluated on the validation data. And as is shown here, the cost function V1 will decrease with the increasing number of the parameters, which is this blue. However, each parameter carries a variance penalty that will contribute with this factor. So this cost function has two contributions. So it's why this cost function can be used for understanding if your parameter was selected in an appropriate way. Let's go ahead to finish. Okay, another important, we will see that during our identification experiment, we will obtain different models. So how you can compare different model structures, of course, is something that we are not really performing, but in principle, we are using the loss function prediction error method loss function as a measure of the model quality. So normally for models of increasing order, the value of the loss function will decrease monotonically, is because you know from the previous slide, I will show here again, if you are depicting the cost function V1 for the number of parameters, the cost function has a behavior like this. So it's decreasing when the number of parameters, sorry, I'm completing the axis. It should be clear because when you improve the number of parameters, your data are described, your model fits your data in a better way. So when you improve the number of parameters, your model is describing your data in a better way. So let's assume. So the problem here is to find the lowest model order that gives a significant decrease of the loss function. So normally in practice, you should select the order that leads you to obtain a significant reduction of the cost function. And normally, if you want to perform it, to check it in a statistical way, you, for example, consider the loss function for two model orders, P1 and P2. For example, as in the previous case, one order was 3 and the second order was 5. So you built this new variable, x. X is defined by the number of data, and this relative ratio, V1 minus V12, so with the different number of order divided by V12. And it can be shown that if this function has a chi-square distribution with P2 minus P1 degrees of freedom, you need to select P1. So P1 is the correct order if this function, new variable, is lower than a chi-square distribution for a given significant level. But if this function is not, this equation is not verified, so P2 is selected. So it's something that if you want to check if your model, which is the best order of your model, you should perform this statistical test if you want to do it. It's something, it's not really required, but is a principle, is the principle which can be used for determining if your model is right. Another approach is to formulate a criterion that is another function of a loss function, but also penalizes the model order. So in general, we will see that there are, as for the previous case, this one, there are other different penalty function that helps you to understand the correct order, which is the most appropriate model order. So normally this function is, as we saw in the previous case, this function in general is a function of V1, so is linked to the prediction error, and there is a factor which penalizes the model order. So B is a function that should increase when the model order increases, but also should decrease to 0 when the number of data tends to infinity. So there are some, in literature, we have different examples of penalty functions. I'm showing here this function because they are implemented in the system identification toolbox. There is the first cost function, which is called the Akaike information criterion. Is indicated with the acronym AIC. AIC depends on the number P, the order of the model, and is built in this way. So V1 multiplied 1 plus 2 divided by n. So as you can see here, it follows the general shape of a penalty function. In this case, beta is equal to, very simple, is a linear penalty of your model order. There is another penalty function which is called final prediction error, FPE. FPE is a little bit different because, as you can see here, it penalizes the product between the cost functions B1 and something that depends in a bilinear way with respect to the penalty of the model order. It's something different. We will see that every penalty function indicates a different model order. So it should be your task to check which is the real, the most appropriate model order. We will see that there are, in the system identification toolbox, there are we will have 3 suggestions of the model order. So which one is the best? I don't know. We should check it. So normally you take the 3 models suggested with from these 3 penalty functions, and then you perform, for example, the statistical tests on the residuals. Is a good way for checking your model. Which is the best one? But we will see later in so the third is the third penalty function is as you can notice here is quite close to the archaic information criterion, because as you can see here is V1 multiplied at 1, but instead of 2 of the archaic information criterion, this is 2 in the archaic information criterion. So normally when n is bigger than 100, and if you remember how to compute the logarithm, this quantity is bigger than 2. So it means that what? This penalty function penalizes the model order in a higher way. So normally, minimum description length is suggesting orders for your model that are more smaller. Perhaps the archaic information criterion can suggest, I don't know, an order for your model of 5, and maybe the minimum description length is suggesting 2 or 3. So which one is the correct answer? I don't know, because it comes from different theories. So is your task to understand which indication is the most appropriate. So, as is remarked here, the archaic information criterion, and there is another property. Archaic information criterion and the final prediction error are asymptotically equivalent, but it can be shown that both will tend to choose too high model order. So normally, the previous one are suggesting models of a bigger order than the minimum description length. So it's as a general suggestion, please consider all possible indications from these indices, from these performance indices, in order to select the best one. But we will see an example. And the minimum description length yields to estimates that are consistent. So the physical insight might significantly simplify the model order selection. So another way for having a suggestion on the model order perhaps can derive from the physical. Physical insight means that you should understand the physics behind your process. For example, you know that the data are generated by I don't know, a DC motor. So you know from the theory that the DC motor only the electrical part has 2 poles, and the mechanical part can have 1 or 2 poles, so the order of your process can be 3 or 4. So this is the physical insight. I don't know, is a thermic process, for example, the heating system is related with the third order of a derivative. So perhaps the order is 3 of a heating system, I don't know. But in principle, you should have a minimum of a physical insight. Of course, if you remember which laws are ruling your process. This is the problem, because perhaps the process, the system you are considering is very, very complicated, and sometimes you don't know the physical laws that are describing, that are modeling your process. Perhaps it's something very complicated. So it's normal. The task is not very easy. Let's go ahead. This is a typical behavior. For example, we have the loss. This is the behavior of V1 that is asymptotic decreasing, and then we have a second graph is the archaic information criterion, and the final prediction error is this one. So as you can see here, so the loss function is asymptotically decreasing. So perhaps from the inspection of the cost function, you will select an order of 6, because the minimum is reached only for the higher order 6. For example, archaic information criterion can have a minimum of 4, but the last one, the final prediction error, is 2. So which is the correct order? We can use other performance indices. For example, we can use the analysis of the residuals in order to understand which is the most appropriate order, because every performance indices is suggesting a different order, 6, 4, 2. But which is the most appropriate? So let's go, for example, from the residual analysis. Away. The other one is, we will use this, for example, can be the pole 0 to see from the pole 0 cancellations. So in order to understand which is from the indication. So these cost functions are saying possible model orders can be 6, 4, 2. So we will identify 3 models in this case, and then we will examine, for example, the residuals or the pole 0 plot. So it's a way for understanding which is the most appropriate. It's very difficult, so the task of the... So in order to summarize this part, so many different tests can be performed to verify the validity of a model. So normally, as a suggestion, try the simple model. The choice of an appropriate model structure, when we say model structure, it refers to the model order, can be based on statistical tests on the residuals, if you remember, autocovariance, cross-covariance, and to have a suggestion on the appropriate model order, you can use the archaic information criterion final prediction error, or the model description, minimum description length. Cross-validation is a good approach that should be used if there is a sufficient amount of data. So it means sufficient amount of data normally when n should be bigger than, let's say, several thousand. Is like an indication. Of course, it's like a magic number. Normally, for the identification, you need at least several thousand of data. And most tests, as we will see in the next lecture, are implemented in the system identification toolbox for MATLAB. It's available since 1990, I think 98, 99. And of course, you can check here, for example, if you notice, we can see here that the order is 1. And if you notice the order is 1, you have an autocorrelation of the residual that it's saying that the residual is not white. So not, I put here a note, not white. If you remember, if the model order is appropriate, this graph, the autocorrelation is, if you remember, if the expected value of epsilon you are performing this test, of course, you can plot only the positive part because is symmetric with respect to the x-axis, the y-axis. So, and if you remember, if epsilon is white, this quantity should be a Gaussian process in between these two thresholds. And also this is the cross correlation. It's very interesting because this is the expected value of E of epsilon of t multiplied by U or U. Of course, tau, it can be only positive, and can be positive, negative, also 0, because epsilon, if your process is white, epsilon should be uncorrelated with respect to the input. And you can notice here that for n equal to 2, you have that the autocorrelation, so epsilon is white. Epsilon is white, and epsilon is uncorrelated . Uncorrelated with respect to U. So this means that perhaps the right order let's say right, I don't know, is 2. So you check all these these graphs on the for every order. So 2, 4, if you remember, the order suggested by the penalty functions, and let's say the lower order that gives you a white and uncorrelated residual means that perhaps this is the right order. It's quite complicated. You need to check different properties, but is we will try a complete test, a complete experiment. And also you can see here there is a comparison of the simulated output and the predicted. You can see here that the result is very poor because the simulated output, this should be the simulated of the model, and this should be the real output. So it's totally different from a very simple. You can see here that the V1 is quite high. V1 is what we call fit 3.82, and for a model order 2, you can see here that the predicted or the simulated output is closer to the real one. So is from a very simple insight, you can see here that is following quite in an accurate way the measured output, and you can also see that here the V1 is lower, is 1.14 with respect to, is about half 1.14 with respect to the 3.8. So you have a very high decrease of your cost function. And of course, this is performed on the estimation data. Let's check. With respect to the validation data, is even worse. If you can see here, the fit is bigger. V1 is 4. Of course, when you are using validation data, the performances can be slightly worse than the estimation data. You can see here that for a model 2, the fit is slightly worse, 1.23 with respect to the 1.14, but not so bad. So it means that a model of order 2 can be good, can be fine for you. It's very simple. 1 is not enough. 1 means there is only one pole. And then, again, we can check, again, the cost function. And in fact, if you remember, the final prediction error suggested a right order of 2, which was the right one. Perhaps is the one you should have selected, rather than order 4 or checking the loss function V1. This is again the V1 6. So you can neglect the suggestion of a model order 4 and 6. So let's keep the order the lowest order 2. And then let's try to check, for example, this is a plot, pay attention, because I'm checking here there is also indicated the uncertainty of your this is not a pole with a zero, but is a pole with its uncertainty. So this is, in fact, you have an order 2 with 2 poles and 1 zero. And check that if you consider, for example, a model order 3, what does happen? There is like a pole zero cancellation. So it means that you don't need to include an extra pole. So 3 is too high in your model because you have a cancellation. You have the same zero here, but if you add a pole, the model introduces a zero, which is not perfectly superimposed to the pole, but is quite close. Is normal. Is a typical situation. You cannot expect due to the uncertainty that the zero, which is included in the model, is perfectly aligned with your pole. Is close due to the noise. But this is an important indication that a model order 3 is too high. So please do not select an order 3. I think is not always the case that the indication of higher order is wrong is always so clear, but in some cases we will see that you have, or you should understand that is something that perhaps 3 is too high for your model. Okay.